Hey students, let's finish up our discussion of titration curves and their calculations. And so today we're going to look at the pH at equivalence point, indicators, which I mentioned in the previous video, but I want to show you some pictures that'll help. And then the titration curves for polyprotic acids, which we're also exploring in lab. And you're generating one for phosphoric acid. Okay, so this was the picture that we talked about from the previous video lecture. Remember that there's one important key concept. When you have a strong acid plus strong base to make salt and water, okay, the salt that you're forming will always be neutral. Why is that? Because, for example, if you have HCl plus NaOH, oops, getting ahead of myself there. The salt that you make in this example will be sodium chloride. So the conjugate base is always the conjugate of the strong acid. And the conjugate then base of a strong acid is a neutral. So always these will have in their titration curves and calculations, the pH at equivalence will be 7. No matter if it's HCl plus NaOH, HBr plus NaOH, nitric acid, that's the one that your book uses in their sample calculations, nitric plus NaOH. That salt, sodium nitrate, nitrate ion, neutral. So the pH at equivalence point is 7. Now, at the end of this video, we'll be looking at how this plays into indicators. So we'll come back to that concept. Okay, so that was that one. Here's the other one that we left off. Let's just review key highlights. Note that on my previous video, because I was using a different reference, the pKa that I have in my slides is 4.87. I know on here it's 4.89. It's just a different references will have can have a slightly different Ka and then you have a slightly different pKa. Okay, so we started off with a pH here, which we calculated in the previous video. We talked about how along the way, this buffer region, so the buffer region is a region of partial neutralization. And that will equal a buffer region. So that's buffer because you have a mixture of your weak acid and conjugate base in there. And then we can use Henderson-Hasselbalch to do calculations in that region. So in the previous video, we talked about what's the pH after 10 mils of base are added, which would put us somewhere in here. So we were below the pKa, which makes sense on the graph. And then we did the all-important 20 milliliters. Notice if it takes 40 to reach equivalence, at 20 mils, at half volume, so at 20 mils, which is half volume to equivalence volume. Half neutralization is another way of writing it. pH equals pKa. So if you know how much it takes to get to equivalence point, half of that pH equals pKa. So you don't have to do all those lengthy calculations. if you can spot that half volume, which is why I highly recommended that you always determine the volume of base that you need for equivalence point. And you can always use the expression MAVA equals MBVB because the mole ratio will be 1:1. Okay, so what today's video is going to focus on is why is this pH 8.80? So let's go to do that. So the pH at equivalence. How do we go about finding that? So we have HPR plus NaOH, NaPr plus water. And our Ka that I was using was 1.34 times 10 to the negative 4. Let me make sure that that was the number. Or was it negative 5? Hold up. Sorry, a minute. Yeah, it's negative 5. I would still do this in class, so it's okay. Makes it more natural, I guess, to kind of pause and think about things. Okay, so our pKa with that value is the 4.87. All right, so here's the thing. Here were our numbers. We had 40 mils at 0.1 molar of acid and 40 mils of 0.1 molar of base. That's the definition of equivalence point. They are fully neutralized. So how did I get this number of 40 mils for the base? Was from MAVA equals MBVB. Okay, so now let's find our millimoles. Remember, we just multiply them. That's the nice part about millimoles. And then, who's our limiting reagent now is, well, they're stoichiometrically equal. They both run out at the same time. But that will always be true at equivalence because remember, at equivalence, you only have salt water. I'm ignoring the 4 millimoles of water that are formed. We just don't need that number, so why complicate things? Now, unlike NaCl, NaPr is not neutral. Okay, NaPr, Na plus, Pr minus. Pr is a basic salt. If you have to, go rewatch the video on basic salts. Okay, so now the question is, what is our pH? How do we find the pH of a basic salt? So that's the video lecture on basic salts. So let's see how much you remember of it. But if it's not sounding remotely familiar, go back and watch that video. Pr minus is a base then. It's going to react with water. It's a weak base, but it's going to form hydroxide. Now, with basic salts, they do form the weak acid too, but who dominates? Hydroxide dominates. It's a strong base, right? So this guy is going to dominate the pH of this. So what we have to do now is, once we get the correct equation, is we are going to have to set up our ice chart as a pH of a base. So here's the interesting part on this, is that, and I think it is hard for students, is that for our bases, or weak acids, weak bases, we have to have concentration. We have to have molarity to do this. Remember our ice charts? Molarity. So I'm going to have to take this 4 millimolar and convert it to the molarity of this guy. So if I take the 4 millimolar, as I showed in the previous video, we can find the concentration by dividing by our total volume in milliliters. Let's note, we started with 40 mils of the acid and we added it to 40 mils of the base. So what does that mean? That we have a total of 80 milliliters. So 4 divided by 80 is 0.05 molar. Now this has a lot of sig figs, so it's going to have like that. And then once we get here, if you can get here, you can finish this problem. So this is minus x plus x plus x. So then we have our x squared over 0.05000 minus x equals, and I'm going to take a minute for you to think about what this has to equal. And hopefully you yelled out, scaring your pets or friends at home, that you yelled out, I need KB. So KB equals KW divided by KA. Let's see what we get. .5 times 10 to the negative 10. And for sure that's tiny, so I can ignore x. So this last part, these hopefully should seem easy at some point once the setup is there. So we should get our x value. That's hydroxide ion. I got 6.1 times 10 to the negative 6. Then that gives us a POH, and then we need a pH. 5.21. And then I'm going to subtract that from 14. 8.79. Which, remember, our Ka was just a little bit different than the one from that book, which is the 8.80 that's shown on the graph. And I really believe pH of equivalence is one of the hardest calculations we do the whole year, because it has everything. It has an equation, neutralization. It has finding essentially stoichiometry. It has pH of a base. It has setting up that second equation. So this is hard, but I'm hoping that you have an opportunity to really practice these as you do your homework and feel comfortable with them. And then you can be really proud of yourself in regards to how much chemistry you have learned over the full year. Okay. I had some blank slides in there. So what I wanted to show you is something I alluded to, in the previous video, was that equivalence points do not necessarily correspond to where you're going to get the color change for your indicators. So there's all sorts of indicators. Phenolphthaleins are our most famous one. It itself is an acid, and it has a color change band where its weak acid is one color, and then the conjugate base is a different color. And if you notice, it goes from light pink to really dark pink. And so its pH range is between 8 and 10. So if you're at a pH of 10, it's that really dark pink color, fuchsia color. If it's a light pink, then you're closer to pH 8. Okay, so I really enjoy, here's some other indicators from that graph, or picture, I should say, graphic. Phenolphthaleins are most famous, but there's also other ones. So this is the color change of bromophenol blue. Okay, so let's look at just phenolphthalein. Don't worry about the methyl red on this picture. Here's phenolphthalein, and here's our strong acid, strong base titration curve with the pH at 7. So using phenolphthalein is colorless at 7. If you add one more little drop, then you could still be below pH 8 where it's going to start turning pink. So it's still colorless. But the more drops you add after equivalence, if you're not careful, you can completely bypass the light pink color and come up here to the fuchsia color. So this graphic really explains why it's so difficult to get that light pink color, because you're in that steeply rising part of the graph. Weak acid and strong base for propanoic acid, the equivalence point would already be pink, okay, for that particular indicator. Okay, and then one other comment, and I won't stress this. Here's a weak base, strong acid titration curve. So this is just an FYI. Notice in a weak base, we start off with a high pH and then it drops, but you see the overall idea is still the same, that you keep adding and adding, and then you reach equivalence point. The one thing to consider on why the equivalence point is low is back to our idea pH of salts, that ammonium ion is an acidic salt. And then everything applies that within this range, that's equivalence point. And then here at the midpoint, pH equals pKa. Okay. We won't do calculations for that category. It just gets to be too much. So I'd like you to focus on your strong acid, strong base, weak acid, strong base. But then, if you're given a weak base, strong acid, if you look at the curve, that you shouldn't be intimidated, that you can see that it's just the reverse because you're starting off at a high pH. But we won't do any calculations for this. Okay, lastly, polyprotic acids. We won't, this I want you to know in concept, but no calculations. But I always have a graph like this. This is what you are going to practice in 201L. with phosphoric acid. Okay, so H2SO3 is a weak polyprotic acid. It's not sulfuric, it's sulfurous. All right, so with that in mind, make sure you understand that this is a weak acid. And then go back if you're not sure of what we're up to here. I did do a video lecture on polyprotic acids, and that was one that a lot of you have not looked at. So remember, I can kind of watch you guys a little bit, or actually a lot, on what you're viewing. So that one's not as highly viewed. And so you probably should go back and take a look at that. So let me show you something that is important. I know it feels like I can spy on you online a little bit more. Okay, so for this, there's two equations. H2SO3 plus NaOH. Okay, remember, our acids always lose one proton at a time. Okay, so our first scenario is with H2SO3 and its conjugate HSO3 minus. Okay, so looking closely at that, here's our first equivalence point. Wasn't so great at writing that as a straight line. Let me try one more time. Too much coffee this morning. Oh, I'm not sure I can do that well. Oh, okay, that was a little better. Okay, that was a lot of pressure. Okay, so there's our first equivalence point. And let's kind of highlight what we're seeing. We start off with acid only. We end up with its conjugate base only. And then we have this halfway point where acid and conjugate base are equal and pH equals pKa. So the first pKa is 1.85. Another highlight then would be that this acid and base pairing would be an appropriate buffer between 0.85 and 2.85, which would be highlighted on the graph, this buffer region here. Okay. The second buffer is HSO3 minus plus more base, so continuing in the titration to give, and is it okay if I ignore the sodium ion? So it'll just be SO3 2 minus plus hydroxide. So the next buffer region is SO3 minus with sulfite ion. That pKa2 is 7.19. Okay, so that then is another buffer region here, which would be in the range of, oops, I think I see it, kept it, 6.19 through 8.19. Okay, so 6.19 through 8.19. And that is a completely different buffer system. So I want you to realize that you don't mix and match these. So there is no such thing as a buffer with H2SO3 and SO3 2 minus. They are not a buffer. Okay, and then the second equivalence point is the second midpoint there. What you should notice is that the pH of the first equivalence point is still acidic, and that means that HSO3 minus is still an acid. So that's what's a little bit different from polyprotic acids, is that we really only get to a basic pH with if it's diprotic with the second buffer system. Okay, so sulfite is basic, but HSO, monohydrogen sulfite, is still acidic. The other thing you should notice is that to find pKa2, so to find this one, I could take the equivalence points and average them. Or if I know the two pKa's, like here, I could find the pH at first equivalence point by taking 1/2 of 1.85 plus 7.19. So this graph would be really important for your lab. And those of you going on in biology and biochemistry, we use these all the time to talk about amino acids. So this is important. What I won't have you do is do all the calculations we did on the previous ones, but for sure expect to answer questions on where the pKa's are, where the equivalence points are in this polyprotic acid. Also understand that it's two separate buffer regions. One buffer is H2SO3 and HSO3 minus. That's a buffer range around 1.85. And then the second one is HSO3 minus and sulfite, SO3 2 minus. That's a buffer region within 7.19. Let me give you an example. Physiological pH in your body is 7.4. So which of these two buffer systems would be appropriate in the body? Well, not the first one. 1.85 is way too far. The second one is okay because 7.4 falls in the range of 6.19 to 8.19.